Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to take up the sixth numerical on detection and estimation. Please note it is a numerical on matched filter receiver. Let me read out the question first. A finite energy signal S of t is given by S of t equals capital A over the time duration 0 to capital T and 0 otherwise. Determine the spectrum of the output of the filter matched to S of t. Right, let me start with the solution part here. Let me rewrite the equation for S of t here. We are told that this signal is given as an input to a matched filter which is matched to the signal S of t itself. Let me draw a diagram for that. Right, this is the diagram for the matched filter where H optimum of t is the impulse response of the matched filter, S of t is the input to the matched filter and S naught of t is the output of the matched filter. As per the diagram shown here, the output of the matched filter can be written as S naught of t equals S of t into H optimum of t. Let me take Fourier transform on both sides of this equation. I'll call this as equation 1 here. This would now become S naught of f equals S of f multiplied by H optimum of f. Please note, I have already discussed matched filter receivers in one of my previous videos. If you have not yet watched that video, I highly recommend you to watch that by clicking on the link shown on the top right corner right now, or I'll leave the link of the same in the video description below. As per the theory, the value of H optimum of f is given by S star of f into e to the power of minus j 2 pi f capital T. Let me now substitute this, which I will call equation 3, and the previous equation as equation 2. So, I will substitute equation 3 into equation 2. Therefore, S naught of f is equal to S of f into S star of f into e to the power of minus j 2 pi f capital T. Here S of f into S star of f is nothing but magnitude square of S of f into e to the power of minus j 2 pi f capital T. I'll call this as equation 4. Now, in the equation 4 RHS, the only unknown quantity is S of f. Let us now try to find that. We know that S of f is the Fourier transform of S of t. So, I'll write it as, and the relation between S of f and S of t can be given by the Fourier transform expression. S of f is equal to integral minus infinity to plus infinity S of t into e to the power of minus j 2 pi f small t into dt. Here S of t is the input signal as per the equation given here. And if you look at this equation carefully, you will understand that it is a rectangular function having an amplitude a and is defined over the interval 0 to capital T. Therefore, this equation now reduces to integral 0 to capital T, value of S of t is a, and the remaining part of the equation is retained as it is. Let me now rearrange this equation. Right. Let us now integrate e to the power of minus j 2 pi f t. We know that integration of e to the power of x is equal to e to the power of x divided by coefficient of x. So, this would become a into e to the power of minus j 2 pi f t divided by minus j 2 pi f. Applying the limits, we have 0 and capital T. Let me apply the limits. This will be a divided by minus j 2 pi f into e to the power of minus j 2 pi f capital T minus of e to the power of 0. This will be a divided by, there is a negative sign here, and I will take e to the power of 0 to this particular place. So, this will be plus j 2 pi f multiplied by e to the power of 0 minus e to the power of minus j 2 pi f into capital T. So, I will reduce this to the form. Here you can see we have e to the power of minus j 2 pi ft. So, I will take one of the terms here as common. That is, I am going to take e to the power of minus j pi f capital T as the common. E to the power of 0 is 1, and therefore, this term which is taken as common will come to the denominator here. This is minus j pi f capital T minus of e to the power of minus j pi f capital T. So, this will simplify to a divided by j 2 pi f into, the denominator is taken to the numerator. So, e to the power of minus j pi ft becomes e to the power of plus j pi ft. Then we have minus of e to the power of minus j pi ft. Then we have e to the power of minus j pi ft. Now, I am going to make more modification. I am going to retain pi and f here, and I am going to take 2 into j to the denominator here. So, this will be e to the power of j pi f capital T minus e to the power of minus j pi f capital T divided by 2 into j. Then we have e to the power of minus j pi f capital T. Now, you look at this term, this is equal to sine of pi f capital T. Therefore, the expression for s of f reduces to, this is s of f, please note, it is a divided by pi into f into sine of pi f capital T into e to the power of minus j pi f capital T. Now, I am going to introduce t in the numerator here and the denominator here. So, this will be a into t into sine of pi f capital T divided by pi f capital T into e to the power of minus j pi f capital T. Okay. So, this is the expression for s of f. Therefore, the value which we are seeking after, which is magnitude square of s of f, will become at into sine of pi f capital T divided by pi f capital T whole square. The exponential term here is eliminated because we are going to take the magnitude square of s of f here. Let me call this as equation 5. Now, we have obtained the value for magnitude square of s of f. So, let us now go back and substitute it back into equation 4 to obtain the spectrum of the output signal. S naught of f is equal to magnitude of s of f square into e to the power of minus j 2 pi f capital T, which reduces to at into sine of pi f capital T divided by pi f capital T whole square multiplied by e to the power of minus j 2 pi f capital T. This is the answer for the spectrum of the output of the matched filter, which is matched to the signal S of f. Right. That is the end of this numerical. If you like this video, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.